Hi everybody, a couple quick administrative announcements before we get started. A few people reached out with the same question regarding the homework, which tells me I wasn't very clear with the instructions. So to elaborate, I do want you to submit just one PDF file with all of your responses to the homework questions. And you can do that by copying and pasting the tables and charts and graphics you create using whatever software you use into a word processing program like Microsoft Word or OpenOffice, and then printing or saving that document to a PDF. Again, you should just submit one PDF file with all your responses. Second, I think we covered a lot of material last lecture, which was great. For some of you, you may have already been familiar with the material. For others of you, that material may have been brand new, but it was a lot. And looking at the amount of material that's remaining to cover this semester, I think we can afford to slow down the pace a little. So lectures will not be as content heavy moving forward. They'll be a little shorter time-wise, and we'll still cover all of the topics that are necessary for this course, and should we need to, we can always readjust the pace. But I just wanted to give you that heads up. So today's lecture is going to be on exploratory data analysis. And if you're unfamiliar with that, this is a process that takes place after you've received your data set, before you start to answer your research question. So you've received your data set, either you've collected it yourself or you've gotten it from someone else, and you just want to explore it. That's the whole idea behind EDA. I had a boss who used to do this by just, in his words, he used a program called Tableau, which, if you're not familiar, is just a tool that makes it really easy to create visualizations and graphs. You click and drag the variable, it'll make the graph for you, and you can further modify the graph to highlight whatever insight or finding you want to communicate. So in his words, he would just mash variables together in Tableau and see what he found that was interesting. That is one way to approach EDA. Other people are more methodical about it. They'll think about the types of variables in their data set, what types of graphs and visualizations might be most clear and informative to them. They'll create those visualizations or tables, see what insights there are, if any, and then further modify those visualizations to communicate those results. There's really no right way to go about EDA, and this is definitely more towards the art side of statistics. But in this lecture, we're just going to cover a few different approaches, and I hope you continue to explore these on your own and come up with your own opinions and thoughts as to the best ways to go about EDA. So we're going to start with univariate analyses, which, as you can probably tell from the prefix and root of the word, means one variable at a time, and we'll move on to bivariate or two variable at a time analysis, which is really about communicating the relationships between variables. So you're much more limited in univariate analysis in terms of what you can do, but there's a lot of possibility for bivariate analysis, and there's even multivariate analysis where you're incorporating several variables, although you will have, generally speaking, when you do create a visual that incorporates more than two variables, you have identified the insight prior to creating the visual. And now you're just communicating it with a third variable. And I actually have some examples of that at the end of this presentation. So first, this might be a little pedantic for some of you, but I do want to be clear what I mean when I say variable. So you can think of it as the columns in your data set. So in the MLB data set that you guys are using for your homework, there are columns like player, team, and then various statistics related to baseball, like runs batted in, batting average. Each of those columns represents a single variable with a whole bunch of observations, and each row in that data set you can think of as an observation. So it's at the player level, and then that player has variables such as team, name, and their baseball statistics. And there's a few different ways to categorize the types of variables you use. So one categorization would be independent or dependent. What does that mean? Well, independent variables are assumed to have an effect on dependent variables. And I want to be clear, and some of you may have heard this before. In statistics, generally speaking, the vast majority of the time, we do not examine causal relationships. We say that two variables are related to each other based on some statistical test, but we're not giving a direction to that relationship. So like one common example when you're talking about causal relationships is the ground is wet and it's raining. We know, based on our understanding of the world, that the fact that it's raining causes the ground to be wet. So the raining would be the independent variable, and the ground being wet would be the dependent variable. That's the way we assume that relationship works. However, when you do a statistical test for two categorical variables, which we're not going to get into right now, but we will in future lectures. Let's say you did like a chi-square test, which you shouldn't know what that is just yet. That like I said, we will be covering it in the future. And you say, okay, there is a relationship here. It does not tell you which variable is the dependent and independent variable. You kind of make that assumption in your communication of your research question. So again, to reiterate, you can categorize variables as independent, meaning they have an effect on the dependent variable, but statistical tests do not identify which variable what the causal relationship between two variables are. Just you as the statistician categorize the variables in that way. Another way to categorize variables is as quantitative or qualitative, which you can also tell from the roots of the words. Quantitative just means numerical, having to do with numbers, and qualitative has to do with like text, or in this case more specifically categories. So a quantitative variable would be height, because I can measure it and turn it into a number. A qualitative variable would be gender, because that is, you fall into one of a set number of categories. And you can actually further classify them. Specifically, quantitative variables can be further classified so into discrete or continuous, which we talked about in last lecture very briefly, but continuous just means there's a range of values and it can take on any value within that range. So quantitative variables can be further classified as continuous or discrete, which we alluded to last class. Discrete simply means that there is a distinct set of numbers that variable can take on, whereas continuous means there's a range of values that variable can take on, and it can be anything within the range. So some examples of continuous are like height and weight. You could kind of argue, although people really don't, that those aren't quite continuous because we're limited by our ability to measure height, right? Nobody's measuring like to 1/100th of an inch, right? We're measuring to like half an inch, generally speaking. So in a way, it's somewhat discrete, but in theory, you can be any height out to however many decimal places. So that's the idea behind discrete and continuous. variables. So before we get into univariate analysis, I just want to talk about some guiding principles that I think are helpful when you're starting EDA. Before you even start exploring your individual variables, you should think about your missing data and the reason that that data is missing. And I'll give you an example that I've come across in my research. We study treatment for people who are addicted to opioids. And one dependent variable, to use a term we just learned in the previous slide, that we look at is abstinence, meaning did they use opioids or did they abstain from opioids in that time frame. So that is often measured. Sometimes it's self-reported, but it's often measured through a urine drug screen, which patients will report for. So let's say that I am missing the urine drug screen for certain patients at certain time points. I want you to take a minute now to think about if that missingness is meaningful, or to put in more statistical language, if that missingness is at random or not at random. So hopefully you realize that that missingness isn't quite at random. It's not like it's not like the probability of someone showing up to a urine drug screen is the same for everyone at every point in time. There are a lot of potential reasons that someone might miss a urine drug screen, but at least one is that they were using opioids and as a result failed to show up to their urine drug screen. And so what that tells me as a statistician is I can't delete that data because it is informative to me. It would similarly be a mistake to say that, well, they didn't show up to the urine drug screen, therefore they were not abstinent. Or in other words, they were using opioids, because they may have missed it for a whole host of other reasons. But I do know that that missingness is almost like a category in and of itself, distinct from a positive UDS, which means that they were not abstinent, or a negative UDS. UDS just means urine drug screen, which means that they were abstinent. So, in other words, that missingness is meaningful, and I have to think very carefully about how to handle it. And there is no clear way to handle it. It is an area of research that still needs to be evolved. But I give you that example just to make clear the point that one way to handle missing data, one common way, is to just remove the observation, and that can be a mistake if we think that missingness is informative. And then these remaining 3 points are less about how you do your EDA and more about how you communicate the results of your EDA. So keep it simple is a key guiding principle in any visualization you make. There is this concept of information overload. People can get overwhelmed by the amount of information you give them in a visual, and you want to make your point as simply and clearly as possible. So those are 2 guiding principles, which I mentioned in your homework, that I want you to keep in mind when making those visuals, both clarity and simplicity. And we're going to go over some graphics at the end of this presentation, and I'll comment on how they could be more clear or simple. So let's get into univariate analysis a little bit. There's a few different approaches you could take here, and you don't have to be exhaustive and use every approach on every variable that it applies to. but I did separate out the results into the type of variable you're analyzing. So for quantitative variables, which as a reminder just means variables that take on number values, right? We already covered descriptive statistics. Those are very informative, and it's a good starting point when you're looking at your variables. Again, make sure you include missing data here before, you could, after this analysis, you could make the decision to remove the data if you think it's missing at random. But as you're doing your descriptive statistics, you want to make sure you include all your data. And then to show the quantitative variables in a visual way, these are some very common visualizations you would use. Density plots we saw in the previous lecture show the relative popularity of your data taking on certain values. Histograms do the same thing. I kind of think of histograms as like a lower resolution density plot, because histograms have bins and your data, falling within those bins. The height of each bar in a histogram is you can think of as the probability that your data falls in that bin, whereas a density plot is smoothed. It doesn't have any bins. We talked about box plots in the past with the 5-number summary. Violin plots are kind of like a hybrid in between a box plot and a density plot. So imagine that you made a box plot, but instead of using boxes and the whiskers, you use the density to show the relative popularity along each side. That's sort of the idea behind a violin plot. They're much less common than a box plot. I think if you were to use a violin plot, why not just use a density plot? But I just want you to be aware these are some options for you. The two most popular are definitely histograms and box plots. For qualitative variables, you can make a frequency table. Remember, qualitative just means it takes on, it identifies the category within a group of categories for that observation. So a frequency table is just the count of how often that category appears in your data set. And then to visualize a frequency table, you have a few different choices. I think the 3 most popular ones are bar charts, pie charts, and donut charts. And again, none of these are perfect. It's somewhat subjective what you use, and different people have issues with each of them. And we'll talk more in more detail about what the pros and cons might be. So in bivariate visualization, again, I break it down based on the type of variable you're looking at. So if both your variables are categorical, you don't have a ton of choices, right? There's not many ways to visualize 2 categorical variables. You can make a 2-way frequency table where you list the categories of the first variable on one, let's say the horizontal part of your frequency table, and the variables of the other category on the vertical part of your frequency table, and then you put the counts of each inside the table. And we'll have an example of that in a future slide, so you'll see what I'm talking about. There's also this concept of a mosaic plot, which I'm not a fan of. It's very similar to a frequency table, just visually, but I find it very hard to read. I would not recommend it, but I just want you to be aware, like with violin plot, this is another option that some people use. And then if one of your variables is continuous and the other is categorical, you have a lot of choices. You could do multiple box plots like we saw when we were looking at the age of Oscar winners. You could do overlaying histograms or density plots to see the differences in the distributions between the categories. And then if you have 2 continuous variables, really a scatter plot is the main plot that people would consider. All right, so that was a ton of information. Let's look at specific examples and comment on the application. So this is a simple frequency table, a univariate frequency table. I'm looking at genre, and I see the count of each of them. Visually, it takes me a little longer to digest than a bar plot, donut chart, or pie chart. However, it conveys the exact same information. Let's see this. Let's look at one of those other three graphics instead. So this is very similar, specifically only looking at action and adventure this time, conveying the same type of information for one variable, very easy to read. I would move the labels that you see here into the plot just to make it a little easier to read still. But this is one way to convey that. Some people aren't a huge fan of pie charts just because they think it's visually misleading. It's hard for us to accurately judge the slice of the pie, relatively speaking. And for that reason, they prefer bar charts. But bar charts aren't perfect either because we tend to judge height as more extreme than width, just because of the way our eyes are laid out. That's why, this is just a fun fact, that's why cereal boxes are much taller than they are wide, because marketing executives realize that your eye is more drawn to things that are tall than wide. So it takes up more space on the grocery shelf, and it takes up less space on the grocery shelf, but it attracts your attention because we notice height much more than width, just because of the positioning of our eyes. So, there actually was a statistician who, this is a little bit of a tangent, but there is a famous statistician who actually tried to correct bar charts for this issue, and he came up with where you take a square root of instead of plotting the count, the bar representing the count, it's the square root of the count. So you still have an understanding of where things fall, relatively speaking, but the differences aren't quite as extreme. So here's an example of a bar chart, also by movie genre. I think this conveys a lot of the same information as the frequency table and the pie chart, but it's more quickly absorbed. A few things I would point out is we have movie genre written twice, both in the title and the x-axis. That's redundant. Let's just put it in one place. I tend to prefer the x-axis over the title. And then I think percent of total doesn't necessarily need to be labeled. I think we all know what percentage is with respect to the total. You might want to put raw counts instead of percentages, but I personally think proportions are more informative because I don't have to do any math when I look at it. I know it's out of 100. Whereas with a raw count, I have to do some math to figure out its relative popularity. And in fact, in the frequency table we looked at earlier, it might have been easier to digest with percentages out of 100. All right, so those are a few examples. I think that's it for univariate analysis. Oh, no, we have a histogram coming up. Actually, we have two more plots coming up. So those are some examples for categorical data. Now we're going to move on to quantitative data. So again, we're still on univariate analysis, looking at quantitative data results. And we talked about histograms very briefly last lecture, but the idea behind a histogram, like I said earlier today, is you have these bins and then you count the number of observations that fall within these bins. And the nice thing about this histogram is that it's labeled, so I don't have to constantly move to the axis and figure out how many observations fall within that bin. The labels aren't always necessary depending on the point you're trying to convey. It may not be necessary information, but it could be very helpful. So this is specifically around the revenue movies generate. And you could see, most movies generate, it looks like this is 50 million here, so this would be 2.5 to 25 million. So most movies tend to be below 25 million in revenue, and then it's heavily right skewed. So yeah, I guess you could say these labels aren't super informative, but maybe to other people viewing this chart, they do want to know how many movies fall into each category. And it does overcome that issue we talked about before, where heights tend to be, we view them as more extreme than they actually are. So this just makes it clear the number of movies that fall into each. You might also want to do something that's a higher resolution, like a density plot, where we're estimating the probability across all these values without the bins. Now here's a box plot of the same exact data, same variable, movie revenue. I'm not a huge fan of this one at all for a few reasons. First of all, we talked about how the whisker doesn't always go to the true maximum. The true maximum is right here. Unfortunately, the whisker, it's using that convention of 1.5 times the IQR, and then everything else gets a dot. But look at how many data points are being represented by dots. So this is, a lot of data that is being cut out of the plot, and I'm not really sure it makes sense to call them outliers at this point when there's this many of them. So I definitely think the histogram was a better choice here. I think the title movie revenue could be on the axis as well. I think commas would be good, or just put it in units of millions. That would make it easier to read as well. So those are a couple choices for the more quantitative data. And I know we didn't look at a density plot, but we did see one yesterday. So now we're going to move on to bivariate charts, where you're showing the relationship between variables. So this is a two-way frequency table, much like the frequency table we looked at before had a list of the variable categories and then the count. However, now we break up that count by another set of categories. And looking at this table, I can pretty easily draw some conclusions. So you take a minute right now and tell me what conclusion you're drawing from looking at this table. So hopefully you noticed there's a difference between males and females in terms of whether they prefer dogs or cats or have no preference, right? Females are somewhat evenly split between dogs and cats, whereas males prefer dogs much more than cats. I think one improvement I would make to make this point is to again make it a proportion, because these numbers are relative, and I don't even think that they interviewed the same number of males and females, right? Because there's 46 males in total, and there's something like 54 females. So like these numbers aren't even, I can't even divide by the same number to do the math right. So if they had just turned it into a percentage from the start, it would have been much easier for me to see, well, like 36 out of 46 males preferred dogs, whereas only 22 out of 54 females preferred dogs. So yeah, I think percentages would be very helpful here. Otherwise, I think this visualization is pretty clear. I'm not sure how informative this no preference is, but to other people, that information might be useful. Okay, so this is a real chart that I've made in a paper that I recently, it has not been submitted yet, but I've been working on. And it's a lot of information, so it can be a little overwhelming at first, but don't worry, I'm going to break it down for you. These colors represent the number of substances that people were using when they began treatment. BL just stands for baseline. So either they were using no substances, one substance, or two or more substances. And then we added this overall category, which might have been more confusing than necessary, but this is just if we ignore that variable categories at baseline and just look at everybody overall, regardless. And then these three labels are different studies that were conducted that we have the data for. And that adds a lot of noise to this visualization. I don't know that it was necessary to do this, but we want to convey that this trend holds up across all three categories, because what you see here is that subjects or participants, whatever word you want to use, patients, who come into treatment on no substances tend to have a higher rate of abstinence. And then the more substances they use, their rate of abstinence consistently drops, with one small exception in this study, when people on 2 or more substances had higher abstinence than people on one substance. But generally speaking, the more substances you use, the less likely you are to be abstinent at the 24-week mark. So this graphic is very overwhelming. It's conveying a ton of information, but I like to think we did it pretty simply. Another thing that I want to draw your attention to is the error bars. So I mentioned this in the very first lecture. Good practice for a statistician is not just to convey, your metric in terms of its measure of center, but the uncertainty associated with that metric. So we measured that 50% in this particular study, trust, 50% of the participants who started treatment on no substances were abstinent. However, the truth, because we're making an inference, and we'll talk more about confidence intervals in the future, but the truth we're saying could reasonably be anywhere from, it looks like this is around 38, 39% to 61%. So we're not totally sure where the truth is, but it could be anywhere in these error bars or even outside these error bars. We'll talk about that more when we get into confidence intervals. And the reason the error bars are so informative here is you can see there's no overlap between 0 and 1 category, and then there's only slight overlap between 1 and 2, which tells us that even at the extremes, there's very likely a difference between the abstinence rates based on the categories at baseline. So the error bars can be very informative as well, especially for people who are thinking more critically about your research. All right, so this chart was very noisy. Let's look at one that's a little more simple, that's also related to work I have done in the past. So here I built predictive models. RF is just one type of predictive model. GLMM is another type of predictive model, and we're comparing their performance with this metric, classification rate. And we want to know, we have 2 dependent variables we considered, abstinence and categories. So these are 6 different models, 12 if you consider the random farce and the GLMM as 2 distinct models. So these are the studies I referenced before. So it's always good to reproduce your findings, right? If held up in one study, did it held up in the next study, in the third study? So we have 3 different studies, and we're comparing, how did the RF model compare to the GLM model in terms of their classification rate. And here the error bars are super informative because you could see the RF model outperforms the GLMM model by a huge margin, even accounting for the potential error in our inference. And that's across studies, that's across dependent variables. So hopefully this is a relatively simple way to convey that information to people.